Okay, and we are live. Hi, everyone. Welcome to another VJEC session. And here with us, I have the pleasure to have Dimitri. Hi, Dimitri. How are you?
Hi, Roberto. I'm fine. Good. Excited to be at VJOG. It seems like a lot of people interested in the talk, so let's see how it goes.
Wonderful. Thank you so much for joining. It's a real pleasure to have you here with us. Anyway, for people that are now watching us live on the stream, if you're not into our Slack channel, please join, because then you're able to post live questions to Dimitri during the session, and I'll be happy to relay them to him. If you want to join our Slack channel, please go to our website, virtualjit.com, and then you'll be able to see there a link right on top where you say join the discussion, and then you have a link to have an invite to the Slack channel. You can join there. There is a specific hashtag that you can also join called live session, and I'll be monitoring that to ask questions to Dimitri. So please join, and let's try to have a good discussion on that. So without any further delay, Dimitri is going to talk to us, going to come to us and talk to us about the session called Performance After 8. And it's not actually the time zone or the time, right? It's the JVM version.
You never know.
Yeah, we never know. So Dimitri, I'm going to give control back to you. So whenever you're ready, please, you can start with your introduction and your slides as well. Thank you so much.
All right. Thank you, Roberto, for the intro. I'm going to try screen share. So let's see if that works. If somebody can confirm that they see something, and if I can hit one more thing, which is this. Okay, you see my slides.
Yeah, we got your slides. Awesome.
All right, so let's get started. My name is Dmitry Veslenko, and the title of the talk is Performance After 8. As Roberto hinted, it's actually the release of JDK 8, and I want to take you on a journey on exploring what were the performance changes in the releases after JDK 8. So by now we have 9, 10, 11, 12 is coming in what, couple of weeks. So let's see what's there performance-wise. So before we begin, just 2 words about myself. I work in Switzerland for a company called Ingenious. We are a little company providing services to bigger corporations, so to speak, trying to help them deliver their products better, faster, etc. I'm also one of the disorganizers for 2 unconferences. One is JCREAT, which we call the hottest unconference, Java unconference in the world, because it literally happens in summer on island of Crete. And another one is JALBA, which is the one organized by Maurice Naftulin, and is happening in Edinburgh, Scotland. My Twitter handle is on the slides, but I don't tweet much. So with that done, agenda for the talk gonna be as follows. I'm gonna look quickly at a new release cadence of Java, because that is what brought us frequent releases, and so we have so much new stuff coming very fast. And then we're gonna look at the startup and footprint of the Modular JDK. So I'm gonna hint at modules and see how the modular changes, if they delivered on the promise of faster startup, lower footprint. And then a couple of selected features from mostly from Java 9. I'm going to talk about other releases as well, and why this change is important. What is the performance impact and so on. So let's get started. I don't know how many of you know that. Probably by now everybody knows that Java no longer releases in these big bang releases every 3, 4, 5 years. But rather in the increments, and we have now stable release cadence every 6 months. We get a new release. This is what you see on the slide, the picture of, so we got JDK 9 released September 17, JDK 10 followed in March 2018. In September 18, we got 11, 12 is coming in March this year. September, we're gonna get 13, and so on. The thing to note is that not all releases created equal. So we have a normal JDK releases, which are essentially lasting for 6 months only and are superseded by the next release and essentially end of life by the next release. And we have so-called long-term support releases, LTS releases. And this picture, you see two. One is JDK 11, another one is JDK 17. And my original plan is that the LTS release is a release that is supported for 3 years. That's at least an Oracle statement on their OpenJDK builds of the new releases. Other vendors have different plans and have a longer support. Windows, if I am not mistaken, for instance, the adopt OpenJDK builds of OpenJDK will be supported for about 5 years. So, and that's probably what I think people will be adopting if they would migrate after Java 8, and that they will be jumping to these releases. So essentially you have a blue pill and a red pill, so to speak. You either can jump on every release every 6 months, if you can, if you ship, I don't know, an executable, and then you control the GRE and JDK you run on, and you can influence that. And if you allow yourself, or you run on your own infrastructure and you in total control, you can essentially upgrade every 6 months and get a new version with new features and fixes and performance improvements, etc. Or if you're a big enterprise or work for bigger corporations, you want more stability, you want longer support time, you want tooling to be there for a longer time, you're most likely going to consider long-term support releases. Therefore, this LTS is sort of important. That's the first thing that changed in the JDK release cadence, is actually the time-based releases that happen every 6 months. And second thing was a change in Oracle's policy of distributing the JDK builds. So prior to essentially JDK 11, one would always download a JDK from Oracle. Most of us would just use Oracle JDK build. Well, with 11, they sort of they open source their commercial features, which are now part of the OpenJDK build. But they still keep their JDK. But they provide two builds. So there is an OpenJDK build from Oracle, which is free of charge. You can use it everywhere in testing and development and production. And then there is an Oracle JDK build, which is essentially OpenJDK build without any extra features on, but with service level agreements on it, which means you can use it for development and testing, but you cannot deploy it in production without license. So you have to be aware of that. I provide a couple of links to the blog posts by Simon Ritter from Azul and from Stephen Colburn on this whole release cadence changes and which are your options for your JDK providers. So before it was mostly Oracle and somebody ran an IBM JDK. Now we have Oracle, Red Hat, IBM, Amazon provides OpenJDK builds. There is a community-driven effort, sort of adopt OpenJDK thing, where you can also get the builds. So there's a lot of different options where you can get your JDK. Very important. Okay. With that said, let's move to the meat of the presentation. Back in the day when modularity for Java was announced, one of the primary motivators for it was to cut down on the footprint of the JDK itself, and with that have a slimmer, better, smaller, and with that probably faster JDK image, which will provide those capabilities. So with that, I want to explore how was that achieved or not achieved, or where we stand with that regard. So if you look at the footprint of, I'm comparing here mainly JDK 8 and JDK 11. So if you look at JDK 8, or particular patch 162, download size, and the JDK 11 download size, JDK 11 has a bit bigger download size. Once they installed, JDK 11 is smaller. It used to be that if you would compare it with JDK 9, JDK 9 installer would be over 500 megabytes. And the reason for it, because it had all those modules like Corba and Java EE and other stuff, which was actually deprecated and removed from JDK in JDK 11. So 11 now is a bit smaller than JDK 8, although it's not super slim as like, okay, we have modular stuff, it's slim. There's a lot of new things that are added to the JDK, like compiled module files and stuff, which actually contribute to the size of the image. So that's just one part of the story, the size of the image. So let's look at a simple example. I mean, this is a boring hello world. And what I want to explore with this little program, what is the startup time of the JVM while running it on JDK 8 and then running it on JDK 11, and trying out different features and different things that were delivered in 11 to see if they help improve or make startup times worse. Let's start with simple comparison. Running with two classical versions. We have still our ClassPass. ClassPass is not deprecated. It's still there in 11. Still going to be there probably in JDK 27. Probably will never go away. So let's use as what we have before, what we have in the system. Let's run let's compile basically this class. We have a class compiled and I run it two modes, with minus ClassPass option and with minus jar option. I run it in both JDK 8 and JDK 11. Well, it's more or less the same. As you see, the time is essentially in milliseconds. It's the fastest options in both cases is ClassPass, because you don't need to read and unpack the jar. So it's 58 milliseconds in JDK 8 versus 54 milliseconds JDK 11. 11 wins by a bit, but not by much. If you would take JDK 9 would be way slower, because there were in JDK 9 and 10 there were some regressions that were addressed in 11 with respect to the startup. Okay, that's fair comparison, but you know, what's the point of comparing old features if we are told that we have modules? Let's use modules. So okay, let's use modules. Well, if you try to use modules in both a module pass and module libs, so if you compile your if you add a module info Java to the class and compile it with, so if you create a modular jar and not a normal jar, and then you run the JVM 11 with the module options, it's actually slower. So you see that running it with module pass, for example, with unpacked classes takes 78 milliseconds, and packed in the modular jar is 76 milliseconds. Okay, interesting. Somehow modularization is not bringing fruit here, but hey, this is not everything that was delivered in 9, 10, and 11. So mostly 9, because modularization was done in line. Let's try some more features. Well, what was also added in JDK 11 was, in JDK 9, together with modularization, was a new tool called JLink. And JLink allows you to build a runtime specific to your application. So unlike taking a standalone or vanilla JDK or GRE and then run your application on it, what you can do, you can take the GRE, you can take your application, which is modularized, and hopefully have all the modularized dependencies. You can run the JLink tool, and that will produce a minimized version of the runtime where you will have only modules that your system and that your particular application needs. So no longer extra craft. It's going to be a smaller application in size, and it will contain only modules. So if we do that, we're essentially on par with ClassPass, but we're still not beating the ClassPass. Well, do we have any other options? Let's see. What can we do as well? Well, JDK 9 delivered, back in JDK 9 was called experimental support. I'm not sure if experimental was removed from AOT support, but nonetheless, what AOT stands for is ahead of time compilation. So when you think about Java, you think dynamic compilation, JIT compiler, doing stuff at runtime. Java-C does something, but it doesn't compile your whole application ahead of time into the native binary. What ahead of time compilation allows you to do, it allows you exactly to ahead of time compile your application into sort of a native image. There's a lot of limitations what AOT can do, cannot do. It doesn't support reflection. It has problems with static initializers and classes and stuff. But for this silly little example, we have here the hello world. It can cope with it. So compiling ahead of time this hello world app, we can bring down the startup up to 42 milliseconds. Hooray! Sort of, we finally beating JDK 8, and we can move on. Well, let's explore some more options that are available since JDK 9. And this is CDS, so class data sharing. So what I'm showing here is a feature that essentially was available since JDK 5. And class data sharing was working for classes that were essentially coming with the JDK itself. So if we apply class data sharing, so how you do it with class data sharing, you first run your application, you dump classes, and then once you dump the classes, then you do the second startup, and then you say, use shared classes. So what it does, it loads the classes the first time and then dumps them in a format that allows upon the next startup avoid opening and rescanning jars. So it sort of kind of produces an archive of classes loaded and loads that in way faster way than the other thing. And what you see here, basically, if I do the same class data sharing thing on both JDK 8 and JDK 9, actually applying it in JDK 8 provides the fastest result so far. So JDK 8 can put in 39 milliseconds, whereas with class data sharing and the normal class pass option on JDK 11, we are at 49 milliseconds. So we are not even beating ahead of time compiled version. All right, is that all that we have? Well, let's see. Yes, there is an asterisk here next to the CDS on JDK 11, because in JDK 11, Oracle open-sourced commercial feature, which is called application class data sharing. So if you recall, the class data sharing from Java 5 was working on the JDK classes only, whereas application class data sharing allows you to do the class data sharing trick using the classes that your application uses. So you can actually dump classes of your application and the dependencies, and then use that upon the next startup. And if I recall correctly, when I did this benchmark, I think I actually used application class data sharing for JDK 11. Despite that, it was still not the fastest option. So the fastest option in my tests on JDK 11 was actually ahead of time compiling this little app to achieve the fastest startup time. All right, the question here you would ask, does it matter? It's all less than 100 milliseconds, one way or another. So let's say it's median is like 50 milliseconds. Who cares about 50 milliseconds? And second thing you might ask, well, it's not actually true. If you take any enterprise application and it deploys to JBoss container or something like that, that thing will start for seconds, if not minutes. So 50 milliseconds or a couple millisecond difference between releases is actually not a game changer. Well, there's a classes of applications where this might matter. If you write in some sort of short-lived command line util, so if you want release, or if you're providing client-side applications, like if you run some on JavaFX and stuff, fast booting of the VM and then the application actually matters. With that done, let's move on to something else. I'm going to quickly mention two JEPs here. I hope folks on who are listening to this now know what JEPs are. JEPs is a Java enhancement proposal. This is a simplified, lighter way than the GSR way to propose changes to Java, especially with the faster cadence every 6 months. You cannot go the GSR route. So the changes proposed to Java go through the Java enhancement proposal process, which is way simpler. And so for every bigger change, more or less, there is a dedicated JEP for it. So for instance, JDK 9 shipped with 91 JEPs implemented. just for the statistical curiosity, if you will. So one of those JEPs was JEP 243, Java level JVM compiler interface. This is just a summary from it. But the interesting thing here is that it's essentially an interface from the JVM to the Java world, and allows you to provide an implementation of Java. Let me paraphrase it. So what this thing allows you to do is essentially it provides an interface to the compiler interface. Here is not the Java C compiler; it's a just-in-time compiler, like a hotspot compiler, like C2. And what this thing enables, it enables to have things like Graal JIT compiler to be used instead of C2 compiler. So with that thing shipped, you were able to start using the Graal JIT compiler inside of VM. It also enabled then later to simplify that in JDK 10, that you can actually run it out of the box. You would not have to like build Graal yourself and stuff like this. A second thing I'm going to mention is that in JDK 9, the default garbage collector changed. Prior to JDK 9, so in JDK 8, default collector was parallel GC. In JDK 9, they switched to G1. Well, switching collector might have surprises. So if your application is well-tuned and you use dedicated collector and have specific garbage collector settings, most likely you will not be affected by the change because you're going to still run with your preferred collector. If you, on the other hand, were using a default GC before, you might experience some difference and variations in performance. On this slide, we see a couple of links to different posts of. So one is here. Dragons is the post by Nitzan Warkart, where he explores a journey of a performance regression that he had with JC tools, tracing it on JDK 9, and it turned out to be that the usage of a default collector, because so switching a collector has an effect like each collector has its own bookkeeping differently, and G1 has a different way of doing card marking, and whenever you store anything to a reference somewhere in Java heap, the GC has to know, okay, you wrote to this reference, so this reference is potentially not dead, it should be excluded or included for whatever scanning determine can be garbage collected or not. And that was enough to, on the JC tools, to have a performance regression, because what JC tool does, it implements a bunch of log-free data structures like log-free queues. And what happened in JDK 9 when they were running that, they had lower throughput by virtue of having this bookkeeping inserted by the garbage collector, essentially introducing logs into the code, which was supposed to be log-free. And he shows also in his blog post that switching the garbage collector back to parallel GC fixes the issue. So with that, and also if you are a heavy G1 user, or if you want to stick with G1 collector, you need at least JDK 10. Although it's not a problem because JDK 10 is no longer existing, so you're going to get minimum Java 11 anyway. But there have been a lot of important changes also brought up to JDK 10, and you can read in that blog post of why it's important to go at least to 10. And here I want to mention something else. We have sort of a garbage collector renaissance now started. So in JDK 11 we have essentially, I think it was in JDK 10 when it appeared first. We have or 11, I'm not sure which one. Oracle open sourced their commercial collector, concurrent ZGC. Then we have in JDK 11 added Epsilon GC. It's not actually, it's sort of a garbage collector which doesn't collect garbage. just for clarification, none of the garbage collectors actually collect garbage. They do the memory management. So they do two things. One is allocation management whenever you need to allocate memory. That's the garbage collector duty. And second thing, they maintain the live set. So they copy and remove, evacuate your live objects that attain the live data set, and then they scramble the garbage. So what they actually collect is the live objects and not the garbage. So it's garbage collector is a bit misnomer. And then finally in JDK 12, we're going to have Shenandoah GC by Red Hat, which is another concurrent GC. Concurrent GCs run concurrently with your applications. They have a different set of trade-offs in terms of so they minimize stop the world pauses a lot at the expense of higher CPU usage and stuff. But it's good to see that, because both Shenandoah and ZGC target big heaps. So we are talking about like applications running with hundreds of gigabytes of heaps, and with existing collectors prior to that, we would basically had no chance, because once you have stopped the world on like something like G1 or parallel GC, you can go home and just simply kill VM, because it's gonna take forever. So this is awesome news for all of us. We have lots of choice, and we can play with those new collectors now. All right, one of my favorite, if not the favorite change in release of JDK 9 was compact strings. So what are the compact strings? Here you see an example where I have a very long string copied from Wikipedia, the famous lorem ipsum Latin phrase. And I'm gonna look at the string using Java Object Layout, one of the OpenJDK tools. Awesome tools allow you to see. It's like an X-ray to see through your objects, see what they are made of. So let's have a look. What does the program print if we run it on Java 8? If I run it on Java 8, what I see, I have a single string object with following structure. There is an object header, 12 bytes. There is a character array, which is a value field of a string. There is another 4 bytes, which is an integer hash value. And then we see something funny was lost due to the next object alignment. And then in total, the string instance is 24 bytes. But this is an instance without content. Content, which is the content of the character array here, is this lorem ipsum string, and together, all in all, the total size of this of the object, retained size by this object, is 936 bits. If we run the same on JDK 11, we see the same story with the header. We see two differences. First, the value field from a character array becomes a byte array, and then we have an extra field coder, which is a byte. But we see the instance size didn't change, because before we had lost to the next object alignment was 4 bytes. Now it's now just 3 bytes. We still fit into the 24 byte size. But the total size of bytes is 488. If you recall, it was 936, 488. It's almost 2 times less. So what's the trick? Well, here we see exactly the effects of compact strings. What compact strings JEP did is that they looked at lots of heap dumps, tons of heap dumps out there of real programs, and they realized that bigger portion of the heap dumps are taken by strings and character arrays, and that most of those strings are actually ASCII strings, or at least Latin 1 encoded strings, which means they all fit in 1 byte. Unfortunately, up to JDK 9, Java strings were always UTF-16 encoded, which means the only thing you can basically have 2 bytes per character. And that's where they try to seize the opportunity, and it's like, okay, what if we opportunistically compress the 2-byte characters into 1-byte characters, and if we can do it, we're going to have a memory saving. And it's just this little example shows it is definitely the case. All right, so we have nice reduction in size, provided your strings can be compressed. The very moment you use something outside of Latin 1 encoding, any character like this, the string becomes uncompressible. Okay, so let's look at one benchmark by the way, benchmarks and all the code and slide will be published after the talk. So if you look at the benchmark here, just showing 3 different operations on the string. One is char at, accessing a character inside the compressed string. Another one, converting a string to a lowercase and just comparing 2 strings. So if you run in JDK 8, what we see is that accessing a character on a Latin 1 encoding or UTF-16 encoded string is the same, because strings are encoded the same. They both UTF-16. There is no optimization, so no wonder in that. Creating lowercase, for example, of a string produces the same amount of bytes, but has a different performance. Doesn't matter the number. And checking for equality of strings, whether it's Latin 1 to Latin 1 or Latin 1 to UTF-16, it takes exactly the same time. Now, if you look at JDK 11, accessing a character by index is essentially the same time, which means we don't have a regression. That was one of the biggest concerns of implementing something like compressed strings and enabling it by default. They had to make sure, the performance team at Oracle had to make sure that there are no regressions in the operations like character add and so on. If you want to know more on the journey how they achieve that, I recommend finding one of the talks by Alexei Shipilov, who used to work at Oracle and did most of the work on the compressed strings, and he has amazing stories about how hard was it to do something like it. Just as an example, in order to provide what you see in the third column, for example, I'm running the same with compressed strings disabled, and you can see that numbers differ. And for instance, if we see the lower casing of a string, which was Latin 1, and doing it with compressed strings and without compressed strings, is essentially almost like 1.6 times slower, but it's more than 2 times amount of bytes generated by this operation because we don't compress the string. So string becomes bigger and stuff like that. So the thing is, the switch to the JVM flag to turn off compressed strings is a string. So normally you just add a string flag and there is no problem. Well, how do you add a string flag, which you have to read inside of a string class if you don't have a string? So calling like, Boolean, get Boolean, or something like that will not work, because string needs a string, doesn't work. Even putting unsafe inside doesn't work. So they tried all the different approaches, and at the end, the only thing that worked was creating a constant with compressed strings, I think. So public static final, which is equals bar to the value, I think, and making sure it's not treated as compile time constant. So you have to call a method to make sure the JavaC will not align it and will not elide the constant and remove the code and whatnot. And then at the startup of the VM, let VM write into the side of string class. So it was a necessity to make changes to the VM and the string class to be able to implement something like a switch in this particular case. Tricky business. One more thing I want to point out in this particular slide, if you see the equals, last 2 equals statements on JDK 11, comparing Latin 1 to Latin 1 versus Latin 1 to UTF-16, the second one is way faster. There is a trick, there is a new optimization inside the string, is that because we have a coder field, if 2 strings have a different coder, they cannot be equal. So there is a shortcut, short circuit at the beginning of comparison to see, okay, if strings have different coder, we don't even bother comparing, they cannot be equal. Okay, so this change to string max size has an interesting side effect, in that essentially the amount of characters you could put in a string is now half of what it used to be. It used to be that in JDK 8, the code that you see on the slide would run and produce a value, would not crash, because we allocating maximum size of the character array possible, we write some data to the array, and then you create a string out of this array, which will basically copy a character array and copy the stuff in it. Everything works nice. Note here, I'm writing some Unicode characters, which means it's by definition not compressible into Latin 1. Now, if I run it on JDK 11 with the default options, this will crash because the character array essentially has twice as many bytes as a byte array inside of string. And because it's not compressible, it leads to this very interesting out-of-memory error that which says UTF string size is 2 gig, but it should be less than 1 gig, because that's as many bytes we can fit in. If it's essentially the maximum array of byte array and character array is the same, but if it's UTF-16 string, amount of characters is essentially half of it. So you can get something interesting like this exception. But hey, I mean, who has strings which are 2 gigabytes in size? Hopefully no one. Another change, which was also done to a string, is identify string concat. If you recall, or if you know how a plus operator was implemented in Java prior to JDK 9, was that whenever you would do something like what you see on the slide, whenever you would use a string concatenation and a plus on a string, what it will compile to would be a string builder and the calling append method. So it will be new string builder, append open paren, append current time millis, append another string, and so on at the very end, and then .toString at the end. So that was the default compilation. The worst part of it was done by Java C. So this is a syntactic sugar that we had, but Java C would do it at compile time translated to a string builder, which means the runtime had no chance to no good chance to optimize it. It could recognize, of course, the shape of string builder append methods as saying, okay, there's probably a concatenation, maybe you can optimize it better. So they decided to attack this case and provide a better strategy for implementing string concatenation. So let's compare what was it JDK 8 versus what is it now in JDK 11. So if you compile this class in JDK 8 and then dump it with, and you use Java P to decompile the code, and then just zooming in on the part where of actual concatenation, you will see, I highlighted here in bold, the allocation of a new string builder and then a bunch of append calls, but at the end was a toString call. So exactly what I explained before. Now, if you fast forward to 9, or actually now 11, and you compile, you'll find something interesting like that. So all the string builder stuff is gone now, and we see a single instruction, invoke dynamic. But hold on, invoke dynamic is for, I don't know, language writers. It's not for Java, right? It was added in Java 7. Everybody knows that. Well, actually not. Invoke dynamic is this superpower, a single bytecode instruction that was ever added to Java since Java release 1, was added in JDK 7, originally for other languages that implemented on top of JVM, because they have a different invocation sequences as the ones that supported by invocation modes that are supported by JVM. But then it was sort of kind of used in Java. For instance, JDK 8, we use it for lambdas. So lambdas are implemented with invoke dynamic instruction. The thing is, we cannot have access. So Java C does not emit invoke dynamic instructions. You cannot do it yourself. So there is no access to this feature from the language yet. But if you use something like ASM or ByteBuddy or JavaSys or anything, then you could, if you would do bytecode generation, you have access to this instruction. So what this thing does here is that it calls something which is called make concat with constant, with this interesting signature, which is basically a long a string and an int, and then it returns a string. So if I go back to my code, you see what I'm appending. I'm appending current time millis, which is a long, a string message, and the count. So essentially, that's a long, a string, and an int. And the rest of this thing is actually a constant strings. So as the name suggests, make concat with constants, as you see here, is a bootstrap method from the string concat factory in Java-lang invoke package. And this is enough. It seems like this method is somehow specialized for our use case. Well, in fact, it is. If you see, the signature says it's long string int, and I don't think they could provide all combinations of all types available in the world in their in this method signature. So the actual method is annotated with very magic annotation signature polymorphic, and JVM sort of, it's like templating type of thing where JIT would emit specific versions of the method at runtime that satisfies that signature, which means we can avoid stuff like auto-boxing primitives into objects and other things. This is amazing. Another thing you can see that part of the arguments to this method is this string. This is actually like this is called recipe, I think, if I'm not mistaken. And this string is essentially resembles our string that we want to see at the end, but it has already sort of a string structure. As you see, there's open square bracket, then this weird /u301. This is a placeholder for which one of the parameters would be substituted. In this case, is a current time millis will go there. Then we have another placeholder and another placeholder. But we also have the square bracket closed. We have all the spaces in. We have parens. So what Java did while building a thing, it computed the final presentation of a string without parameters, provided this recipe, and provided the parameters to the call of this thing. All right, so this is all cool. So what will invoke dynamic do? Okay, invoke dynamic works. It is a two-stage process. The very first time invoke dynamic is invoked, it has to so-called bootstrap method, as in this case is make concat with strings, to say, okay, I have no idea whom I'm calling, so please bootstrap method prepare me a thing called call site, which is a result of the bootstrap method, which will tell me from now on whom I have to call. So very first invocation will call the bootstrap method and get a call site, and afterwards call site is cached, which means all subsequent invocations through this invoke dynamic instruction will call directly to the resolved call site. So originally, as I said, it would be done by languages like JRuby, which will resolve whatever object or field that you are calling, and it will, after that, keep calling that thing. But here, it will actually call this make concat with string, which will build the code on the fly at runtime, would build the code that would be necessary to execute our string concatenation. How cool is that, huh? So let's look what it actually means. So if you look inside the string concat factory, you will find that we have actually 6 strategies to implement concatenation. We have 3 ones that are based on bytecode generation, and 3 are based on method handles. So bytecode generations, we have 3 versions based on string builder, which is empty string builder sized and sized exactly, which is more code involved trying to figure out how many bytes we have to allocate to build it. And then we have a method handle combinators, where we have also sized and sized exact versions that are still based on string builder. And the last one is the most interesting one, because this is a method handle inline, which essentially builds a code using method handles that would write a final string that we concatenate directly into the byte buffer, so that then when you need to create a string, you would simply create a string object with provided byte buffer, without copying, without anything, without allocating string builders and other things. And the good story is that this is the default in JDK 9 and 10 and 11. So that's what concatenation looks like. Okay, there's been a lot of words said by me. What does it mean performance-wise? Why do I care? Let's have a look. If I run that code that you've seen on the previous slide with logging, and I run the JMH benchmark, and I would run it on JDK 8 and JDK 11, well, we have about 3 times performance improvement, and we have about more than 5x reduction in the garbage generated. So JDK 8 would allocate 432 bytes while building that single string, and JDK 11 would allocate 80 bytes. And 80 bytes, it's exactly 80 bytes that are needed to produce that string. So it doesn't allocate any single byte, it doesn't waste anything. And then just for comparison, I'm running on the JDK 11 with all other combinations of all other strategies, and they all run slower than the default one. They do allocate more memory. They are not that much slow. For instance, bytecode sized string builder exactly. It's close performance-wise there, and then we even have some very weird performance cliffs, like method handle string builder sized exactly is worse than method handle string builder size. So because the exact size figuring out exactly size of for some objects, like for even for primitives, for example, for doubles and floats, is implemented by calling toString on that thing and then asking string.size. So it's not the most efficient. So the best strategy here is basically JDK, the default in JDK 11. This is awesome. Okay, let me try to speed up a bit. One thing to note, having fast string concatenation doesn't mean that we can be sloppy. That is, we shouldn't go and replace all the code, all the places in our code, and then just throw away, for example, string builders and use everywhere string concatenation, because there might be problems. For instance, here I am concatenating naively in the loop. I'm creating a big string, result string. And then I have the same with using string builder. Well, if you notice, the version on top, which has a warning sign on it, uses something called plus equal. So plus equal operator in Java, and so essentially is mandated by JLS to produce a new string, which means on every iteration of this loop, we cannot collect to the single string object, but instead every iteration here would have to allocate a new string and then add it to a string, and then keeps generating. So if you would run this code, you would see something like that. If you run JDK 8, a naive and proper version, you see we have factor of 5 performance and factor of 15 in garbage generated, because the naive version allocates tons of strings. If we are back to 11, we see there's a big improvement due to compressed strings and how things are handled, but still we have like 2x performance on the table, and it can be way worse if the more iteration, the bigger the strings you're building, of course, and 5x in terms of garbage generated. All right, with that, let's have a look at something else that was added in JDK 9 again, convenience factory methods for collections. What are those? So prior to that, if you want to allocate a list of something, you had things like arrays as list, or you would have to new array list and then keep adding things. So convenience factory methods allow you to create list, set, and map with a single line, essentially, with convenience factory methods. And this thing produces an immutable collection. Well, actually, if you look at what it implements abstract collection, which means it implements collection interface, which is not immutable, but rather read-only view. Because if you try to call any modifying operation on the collection, it will actually throw exception. But OK, so first thing what I'm looking at is what is the footprint of bytes of different and comparing it of calling the new list of, for example, implementation versus what else we have in the system. Like creating empty list. Well, list of returns a bit bigger object. I'll touch in a second why. But this is a single constant for the whole JVM, so it doesn't matter. Creating a single element like list of 1 essentially produces 40 bytes, out of which 16 byte is the actual integer, 24 byte is actually an object. The same as singleton list from old collections. All right, so if we move to two elements, we see the new method produces 56 bytes versus array list having 80 bytes and linked list having 112 bytes. And by the way, you should never ever use linked list in your code again, because it's non-cache friendly and really bad data structure for modern CPUs, and there should be absolutely no use cases to use it unless you're really sure that you need it. And if you go all the way to, for example, like 10 elements, you see that essentially the list of and array list is more or less the same. It's exactly the same because the list of is implemented internally. Is basically there are two implementations in 11. List of 2 elements and list of n elements, and list of elements n elements has an array inside, the same as array list, but array list I think it has another field like mod count or something like that. Therefore, it's like a couple of bytes bigger, but at the end doesn't matter. Now, it's not a correct comparison because list of produces immutable collection versus others don't produce immutable collection. So if we would repeat the previous test and add an unmodifiable list on top of all the other calls, then we see a bit different picture. So we still win a couple more bytes if we go this way. Well, the same can be done for set. Numbers differ, of course, but especially at small number of bytes. For instance, a set of 2 elements of a set of it's just 56 bytes, but the nearest closest to it of hash set, actually 3 set is the next closest, would be 208 bytes, but the hash set would be like 270 bytes, like huge overhead and huge amount of, and they're not, yeah. And there are other things to note here about the new collections. For instance, sets and maps, randomized iteration order. So every time you run a JVM, there will be different seed generated, and every time you would traverse collection, you would get it in different order, which might, in some cases, if you have bigger collections, you would actually iterate over your sets or maps all the time, have a poorer performance than things like hash set or hash map. But that's I would say if you're iterating over your maps all the time, it's probably a wrong data structure to use. Maybe you want a list or something to have like to have a guaranteed iteration order and stuff like that. Anyways, what else I have on the table? Well, we have a stack walking API. Prior to JDK 9, the only way to get to see a stack trace of application, you could use either new exception get stack trace, or you could do thread.get stack trace or get stack traces, dump all stack traces. You had tools, but they were very heavyweight. And you had a couple of use cases sometimes where you need the stack trace at runtime to do things like, for example, checking who's my caller. There was a way to do it in JDK 8 and below, but it was in some comsan misc packages. There were classes that would allow you to do, like getCaller, for instance, was there and implemented in better way, but you would then use an unsupported API on your own. So here what you see is like I'm doing 3 operations, getting a caller class, just looking at the stack depths, and consuming top 10 frames of a stack using JDK 8, basically exception API. And then I'm doing the same using new Stack Walker API. I am updating Stack Walker instance using retained class references because I'm going to get getCaller class. By default, that is not supported, so you have to enable this. And essentially, getCaller class is a single operation, is provided out of the box. And for the rest, you have a walk method. And the walk method has very interesting signature because it doesn't return you a stream or a stack or anything. It receives a lambda, essentially a consumer, and that consumer gets a stream of frames. And the reason for it is that by the time you call in, start walking a stack, JVM cannot give you a snapshot of a stack or anything because the thread will move on. So instead, they say, okay, when you call a walk, we're going to give you a view of the stack, and this is guaranteed to be alive for the duration of your walking. Once your lambda is done, that thing can be, scrambled away. This view of a stack can be thrown away and stuff like that. So Very interesting, very nice API, and very simple to like count is count in the stream. Getting top 10 is getting like top of a stack. And here's the difference in the performance. So time is in microseconds. Like getting a caller class and stack walker and exception is about 30x difference at the stack depth of 10. You see all other things like consuming, like looking at the stack depths, also faster. Looking at the top 10 frames is faster by 6 times. But if you go to stack 100, you can see that the caller class obtaining in stack walker is a constant operation. So it's independent of the depth of the stack. Whereas in exception case, everything is dependent on the stack, because new exception gets stack trace. You have to materialize the whole stack view and give the whole stack trace. And then finally, a stack walker, different things of stack walker, like for example, looking at the stack depths requires you to walk the whole stack frame. So the bigger the stack, the longer it takes, versus picking up top 10 frames is essentially the same in both. So it's cost 5 microseconds in both cases. And the last thing I want to mention quickly, looking at the new APIs, there are tools. There's an Adopt OpenJDK project, JDK API, which can show you differences of what's the API differences in JDK. There's a couple more. There's one from Mark Hoffman, where he shows also API differences between the releases. Finally, Chris Newland, the author of JIT Watch, has an amazing page of hotspot option differences, where first two show the API JDK difference, while the last one is talking about what changed in the hotspot options, which options were deprecated, added, removed, produce warnings, and stuff like that. Awesome job by the guys. Really recommend to look there. Want to talk about one method added in JDK 9, that is arrays mismatch. So what does arrays mismatch do is essentially what you see on the screen in the hand-rolled version of it. It allows you to find a point or an index at which both arrays start differ. If arrays are absolutely the same, if they're equal, then there is no such point. Then this method of arrays mismatch returns -1, meaning they're equal. If, however, there is a point in two arrays they're different, it returns that index. So what I'm comparing here is that I went and copied the implementation of arrays mismatch from the JDK code, as you see, and I pasted it here, and then I'm running JDK code. So essentially, I would expect that it produce absolutely the same results. However, if I run it with different sizes of the arrays, of the prefix size is a common size of both arrays. So I have one array is small, another array is bigger, but the common prefix size is like 10, 100, or 1,000 elements. And if I run that using built-in, then the calling arrays mismatch is very fast. At prefix size 10, both hand roll and built-in cost the same, but already at 100 elements, we have like factor of 3 performance difference. At factor of at 1,000 elements, we are more than 10x. It's actually 12x performance difference. So what's going on here? This method arrays mismatch is intrinsified. So intrinsic means that instead of running Java code on the supported platforms, it will be replaced with specialized assembly code or JIT. It's either direct assembly code or JIT template code. The JIT can then optimize. And what arrays mismatch actually doing? It uses vectorized. It vectorizes that loop of comparing bytes, and instead of comparing the bytes one by one, it compares 8 bytes at a time. Oh, actually, I think it compares more than 8 bytes. It's like compares like 64 bytes at a time or something like that. Anyways, it works bytes in bigger chunks, in bigger strides. That means it reduces amount of traffic of asking, for next memory. Prefetchers work better, etc., etc., etc. We get cool performance. And in closing, we have a 6-month release cycle. Be aware of the different vendors and of the Oracle changing the license on their Oracle JDK build. So you can get an OpenJDK build from Oracle, and that's okay. But if you get an JDK build of Oracle, not OpenJDK build, you might be in trouble if you want to try to use it in production, unless you have a license. So look elsewhere. Look at the blog posts I provide. And for me, one of the coolest things were changes to strings. compact strings and optimized string concat. Those features work amazing together. So we also saw it on the string concat that you have optimized string. So essentially, concat works both better because it has smaller strings. So as a combination, huge win for string manipulation, and hopefully reduces your heap size substantially. We have a bunch of new APIs like Stack Walker, Raise Mismatch, a bunch of others. Use the other resources provided to look what changed, and I hope I at least sparked a little bit of your interest into looking into past JDK 8 release and thinking about upgrading if you are performance curious. And with that, I'm done.
Hey, Dimitri. Wow, that was a wonderful piece of information that you showed up there. Do you mind moving your screen share?
Yes, I will do now. Screen share is removed.
Okay.
You are in full control now.
Yeah. Well, we're both in control. We just wanted to see you. I mean, you might probably be exhausted of all the things that you presented to us. I mean, it was like a wonderful presentation, and we cannot thank you enough for all these piece of information that you collected together for us. So we have a question here from our audience, and basically they're asking if you can share the deck of the slides and where can we find them.
The slides will be a speaker deck. There's a couple of versions of this talk already available on speaker deck. Most recent one was from Code 1 last year, but I will share this deck like after the session.
Yeah,
so,
I mean,
I'll tweet the link, and I'll CC virtual jog so you can retweet it, and then
sure. I mean,
so
you can also send it to me, and I'll send it to the
I'll send it to you as well, so you can send it over Slack.
That
will be absolutely shared, and because especially for the references, there is a lot of material by other people and the research by other people done, especially like differences in JDK API and stuff like that, which is amazing work and very insightful. So you can see like what actually changes, and not from the like top level feature level, but actually on the method level. You know, sometimes you find really awesome discoveries like, wow, I didn't know this class exists or this method exists. Well, can I try it? And
yes.
well, what's going to be there? Yes. Are there any other questions?
Yes. So we have a question from Vladimir. So he's asking, does JIT work for analysis of production system? Not for like 4 or 5 lines long benchmarks, but for a kind of a production app?
Yes, I believe so. Well, JIT works with the JIT compiler log, right? So if you go to the JIT GitHub page, it will tell you how you can collect one. How can you get one? You can essentially enable that, and it will produce the XML-ish structure that essentially unparsable by human. But then you can feed that to JIT and that will work. I remember like half a year ago, so like last summer, support for past JDK 8 was sort of in progress. Because mainly unified logging changes and stuff. So one of the JEPs delivered in JDK 9 was unified logging, where they decided the way JVM logs information is not good, so they decided to unify it, which means GC logs and all other logs changed and broke. So broke all the parsers and stuff. So it costs some overhead to people to do it. But I believe now JIT supports no problem JDK 11, so you can get also like either logs from 8 or from 11 and run it through JIT and it will tell you what was compiled, what was not compiled, what were the problems and stuff like that. JIT is an awesome tool. Especially it has like diagnostics hints where it will say, okay, suggestion, your methods are too big, or your inline budget is too tight, or try changing this flag and stuff like that.
Wonderful.
But I would say that going JIT it's essentially should be like nth step in the performance analysis problems, and as long as you eliminated all other bottlenecks and problem, big things from the table, like big wins and big fat bottlenecks from your system, then you can look into the JIT and say, okay, are my methods too big and stuff like that? Because I think in normal application you will have tons of other problems in a way before that.
Yeah. Let's see if we have any other questions over here. So we have a couple of other. So this one's from Frank. So what was the tool to get the object size? Was it JOL?
JOL, Java Object Layout. I have a link. The link will be in the slides as well. So we'll see in slide deck. So tool was JOL to get a size. Benchmarks were run with JMH. By the way, in 12, the set of JMH benchmarks will be added to JDK. So we will finally have a set of regression performance tests for JDK itself, but they are more proprietary and not based on JMH. But with JMH set of benchmarks coming to JDK, which is also awesome news because we can also learn how to write proper benchmarks. We can peer review benchmarks and we can contribute hopefully to some benchmarks to the JDK to avoid performance regressions.
Mm-hmm. So a follow-up question about that: are you able to use JOL in unit testing?
You can use JOL in everywhere. So I actually used JOL a couple of times to diagnose or look at production problems, like production, like running in a testing environment, deploying JOL as a library, changing your production code, and for instance, like capturing, getting the size of an object. For instance, you hinted that something is very fat, but you're not sure. I mean, you can get a heap down with the other things, but the last thing I did was I got the object, and what you can get graph layout, and you can actually work the whole thing, so you can see what hangs from this object. And sometimes you find some silly reference somewhere which has a static field or something which hangs to the whole system. So you have a tiny little object which turns out to be in size like 1 gigabyte because it holds on to something it shouldn't through a chain of references. And I used that in the past. And yeah.
Cool. And we have another question here.
Yeah.
Yes.
There was one.
Sorry, go ahead.
No. It's okay. There was one comment regarding JOL that due to JDK 9 changes, whenever you run JOL, by default you might see a warning because it uses some operations, whatever. There's like reflection or something like that.
Yeah.
But anyways.
So another question I have over here is, does JLink help for performance?
Well, performance, okay. Aside from the test I did in the startup, my experience with past JDK 8 in production is limited. I did, about 2 months ago, migrated one project from 8 to 11. The main motivator there was end of life of 8, and the second one, support for running in containers, mainly Docker. And so prior to essentially JDK 10, Java wouldn't respect container limits. So like CPU quotas and memory and stuff. It would essentially see past container and start with a bigger default than it allowed to. And this JDK 10 is fixed. So we used essentially 11 for that. And we haven't, because we were deploying in Docker, we were using already JDK sort of image with JDK. So we didn't build image using JLink or anything like that. So I cannot say if JLink helps performance-wise. What it helps to reduce the application size. The one that I showed with JLink, when essentially we went from 300 megabyte JDK by running JLink to 45 megabyte installation where you have only JDK modules that the application uses, plus application modules itself, plus you have a native executable. So another cool thing that JLink provides, it builds you an exe essentially. So on Linux, it builds whatever shell script thing that can run your application, and on Windows, it's going to produce an exe file. So instead of then running Java minus something, minus jar my application, you simply say, hello world.exe, boom, your application is running. Mm-hmm. So this is another cool thing, and so it definitely reduces the footprint, whereas the application will run faster as a whole. I doubt so. I mean, it will definitely help because there's less modules to parse and load at the startup. But other than that, I think, you're running on still the same JIT and same everything. It's not like, there is some magic.
Okay. Well, we are like 10 minutes past the hour. So I think we're going to call it a day. There are a couple of other questions here, so maybe we can take them offline.
Absolutely.
Anyway, thank you so much for being here with us, Dimitri, and for this wonderful presentation that you gave us to us today. We hope that you can return to the VJug soon with another awesome session. And again, thank you for all the audience that was here with us today, watching the session, and all the questions that you asked in the end. So until the next time, we're going to announce the next couple of sessions in the next couple of weeks. So stay tuned for the next VJug session with the next awesome speaker. So see you in a couple of weeks, and thank you so much for watching. Bye bye.
Thanks, Roberto. Thanks, everybody. Bye bye. It was awesome being there. Bye.
Yes.